My task today is to tell you something about simplicity and complexity, and I want to begin by simply asking a question. If we were to walk around this university campus or on the street outside and ask people at random, is the universe simple or is it complicated, then we would get a variety of different answers. If by some misfortune you happen to stop and ask this question of a string theorist or a cosmologist or someone working in quantum gravity, they'd soon be regaling you with wonderful stories about how simple the universe is, and if you just come back in a few years' time, we will have reduced our understanding of the universe to just a single equation, which you can write on the front of your t-shirt. But if by bigger misfortune you were to talk to an economist or a social scientist or even a biologist, they wouldn't talk to you about simplicity or laws of nature or anything like that at all. For them, the universe and the world around us is extraordinarily complicated, and there are all sorts of competing effects vying to dominate what trends emerge. So who's right here? Is the world really simple, like the fundamental physicist would try to persuade you, or is it complicated, like everybody else seems to think? So I want to answer that question, and also along the way show how some important mathematical contributions have been made to the path that leads us to understand the answers to those questions. Well, the picture of the world that thought that it was simple owes a lot to the idea that there are things called laws of nature, that there are simple regularities in nature that dictate how things are going to happen. And this is an ancient idea. It has origins outside of science, and it tended to be fostered in societies with strong monotheistic beliefs and rather rigid systems of statute law. You see, it's a rather simple step from the idea that society is governed by externally imposed rules and regulations to the idea that some omnipotent deity imposes such regulations on the workings of nature. So there is a small step from the idea of God ruling the world to the idea that there are things called laws which do that governance for the deity. But there were interesting counterexamples, as Needham first pointed out long ago, in the Chinese situation of a very sophisticated, scientifically orientated society, huge technological achievements in early times. There is no monotheistic belief. There is no concept of laws of nature, really, in our modern sense. And Needham argued that this was one of the reasons why science, as opposed to technology and the making of devices, never really flourished in early China. So in China there was a battle between two systems of belief, philosophical belief, into the running of the world and of society. There was the view of Li, that is, there were imposed laws from outside, but it was really overtaken by the view that there were sort of naturally emergent principles. So the Confucian philosophy was that everything should work together in some emergent fashion, and the best possible solution, the most harmonious society, should emerge out of this interaction. So this is a model of the world like the ant colony, where order seems to arise spontaneously, rather than a picture where it is imposed from outside by external laws. Well, how might one think about laws in a rather modern, more scientific or computational way? Mathematicians have been interested in trying to define complexity in some convincing fashion for a long time. And when I last looked, there were about 35 different prospective definitions of complexity, and you gradually become persuaded that complexity doesn't have a unique categorization. It's as much a quality as it is a quantity, and you've got to pick your definitions for the purpose to which you want to put them. An interesting approach that gives you one perspective will be to look at two sequences here of zeros and ones, two binary sequences, and ask which of them is ordered and which is disordered. Well, assuming things just go on forever inductively in the same way, it's fairly clear that one might suspect that the first one has an order to it and the second one maybe not, or at least less order. But the interesting question now to ask is, what do you do in your mind when you come to that conclusion? Well, the first sequence, you might say, if you believe it's ordered, one thing that might tell you is that if you want to transmit this sequence, or one that's vastly longer, to your friends on the other side of the world, you don't need to write the sequence out in its entirety. You can replace it by a formula, by a recipe, which is shorter than the sequence itself. And that short recipe contains all the information in the sequence. But as the sequence becomes more and more disordered, increasingly random, in some precise sense, the possibility of having an abbreviated replacement for the sequence becomes more and more challenging. And the abbreviated statement will become longer and longer. So one suggestion that was made by Chaitan and others then is that you might define the random sequence as being one for which no abbreviation exists. So you would have to transmit the entire sequence. There's no formula, there is no abbreviation with the same information content. So this idea was sometimes called compression. So if you can compress the information in the sequence into a shorter formula, we will say that the sequence is non-random. And if you can't, that it's random. There are all sorts of funny consequences of this. You can never prove rigorously that a sequence is incompressible, that it is random. This turns out to be closely connected to Gödel's incompleteness theorem, because the theorem that you might require to produce the next abbreviation of the sequence might be a Gödel undecidable statement. There is a way in which you can think about science in the broadest terms as being the search for compressions in this sense. So if you want a very short definition of science, it's the search for compressions. So if we just go around gathering data about the universe, measuring the positions of planets and stars, tracking objects moment by moment in the solar system, capturing and classifying every conceivable plant and butterfly, I don't think we're doing science. We are collecting information. We start to do science when we do something in addition to that. And that is to find the patterns, the sequences, the compressions within the data. So if we're astronomers, we don't just keep great filing cabinets full of positions of planets at every moment in time, but we find a compression, whether it's Newton or Einstein's laws of motion, which tell you that if you know a position of a planet at one moment, you can predict what the future positions will be at different times. And the nice thing about that is that you can test whether your compression is correct, because you can make the prediction and then see whether it is indeed the correct one. So one of the lessons of this is that the doing of science is about the spotting of patterns, and there are no rules about how you do that. You can dream that you see the patterns, you can see them in the tea leaves in your teacup. There are no rules for the framing of scientific hypotheses. There are, for some people, very strict rules about how you go about testing whether those hypotheses are correct. Well, where does mathematics come into science? people like my wife, who is not a scientist or a mathematician, is often surprised or even annoyed that mathematics seems to be so influential in so many things, and that there is a mathematical aspect of something that she needs to do or she needs to plan. And I think if you were to ask people around the university what is the definition of mathematics, you might be rather frustrated by the answers. If you go into the history department of the university and ask people what history is, there's no doubt. If you go into the department of English or Italian literature and ask them what their subject is, there is no doubt. But if you go into a mathematics department and ask mathematicians what is mathematics, then there is a big argument. And there are whole subsections of the world of philosophy that spend their time trying to answer this question. If somebody were to stop me in the street and ask me what mathematics is, I would say that it's the collection of all possible patterns. And you begin to see then why mathematics is so ubiquitous, why it arises in so many areas of science and human activity. Because so much of that activity is about finding patterns, finding those compressions in the things that we see around us, so we can replace them by rules or formulae or programs or whatever. If you define mathematics like this, then the fact that mathematics works, what Wigner called the unreasonable effectiveness of mathematics, is no longer a mystery at all. It's totally inevitable that mathematics works. It couldn't be otherwise. The world has to contain some patterns, otherwise natural selection could not have operated in the evolutionary process, and we wouldn't be here. So there is no mystery that mathematics describes the world, that the world is mathematical. But the big mystery is why such simple mathematics is so far-reaching, that why such a small number of relatively simple patterns are able to allow us to understand so much of the world around us. There is a mystery because it would be quite possible for the world to be mathematical, in my sense, and for mathematics to be of no practical use. So if almost every mathematical function was non-computable, in Turing's sense, then mathematics would not be very useful algorithmically for making computations. We could prove lots of beautiful existence theorems about mathematical structures in the world, but we wouldn't find mathematics to be very useful. So one of the subsidiary reasons as to why mathematics is so useful in physics and engineering is because there are an awful lot of computable functions. And a computable function is a function which simulates the operation of some device, a computer if you like, and therefore obviously it gives a good description of it. Well, this picture of mathematics as a pattern and the idea of lawfulness and non-random behavior of being able to compress information allows us to draw a sort of quadrilateral of interconnections. So those compressions are really like finding laws of change or of structure, and that tells us that they are equivalent also to patterns or to symmetries. If you went back in physics 300 years ago and you looked at how people carried out their study of physics at the time of Newton and afterwards, they would look at the world, they would see some things that always happened, they would try to describe that using simple mathematics, they would make more predictions, modify the mathematical law, and so on. But in the 20th century, physicists became so impressed by the role of symmetry in physics that the role of symmetry really leads the search for laws of nature rather than arriving on the scene later. So what had happened with symmetry in the 19th century is that people who knew about the conservation of energy and of momentum or electric charge eventually can show that those conservation principles are equivalent to invariances of the laws of nature from one time to another. So it doesn't matter when you carry out your experiment, you'll find the same laws. From one place to another, doesn't matter where you carry out the experiment, and with respect to rotations from one direction to another. So it doesn't matter in what direction you point your laboratory, you will find the same laws. But in the 20th century, the belief in symmetry has become primary, and physicists looking for laws governing elementary particles started to begin with the symmetry. Symmetry having certain nice properties, perhaps that of a simple group, sort of analog of a prime number, so you don't have subgroups where interactions can just talk to themselves without interacting with everybody in the group structure. And these sorts of theories, for historical reasons, have the name gauge theories. So a gauge theory is a theory of interactions built upon invariances. And the four fundamental forces, gravity, the weak interaction, the strong force, and electromagnetism, are all described by gauge theories. And they're very successful gauge theories. The theory of general relativity is accurate to fabulous precision, shown by the binary pulsar. What's unusual about gauge theories is that they don't only tell you how the forces of nature act, but they also dictate that they have to exist and the nature of the particles that they act upon. So this is much more than Newton's laws could ever do. You see, Newton's laws act upon all particles. So Newton begins his description of his laws of nature that all bodies acted upon by no forces remain at rest. So the fact that the laws act on all bodies means that they're not going to be able to tell you anything about the nature of the bodies. But gauge theories are more particular. They act upon classes of identical elementary particles. So it might be all electrons or all particles with electric charge or all photons. And they're then able to tell you something about the nature of those particles and about the nature of their interaction. So the invariance in these cases requires the force to exist. If we take the case of a theory like electromagnetism or gravity, then the simplest invariance that you might require of the laws is that it's the same if you move everything in the same way from one place to another. So a so-called global gauge transformation. So imagine you apply this to something like my hand, then it just moves in the same way to here. But if you want every point in the universe to respect that transformation instantaneously, this seems to violate causality. So suppose you want it to be invariant under something much more restrictive, that you're allowed arbitrary changes of every point. So an arbitrary transformation. That seems completely impossible because my hand would move away into some crazy mixed up collection of atoms. But suppose a force exists, okay, and I wrap an elastic band around my fingers very tightly. It would be possible, if the force had the right properties, for that force to still constrain my hand to remain the same position. So that additional transformation invariance requires the force to exist. So in the case of general relativity, the invariance, as it were, of my hand with respect to being accelerated in a general way requires the force of gravity to exist. So these laws are extraordinarily powerful. They're based upon particular symmetries, and physicists are not really content with the fact that they have four nice, completely working sets of laws, four symmetries. For a long time now, they've been searching for a way to join those symmetries together, to place them inside a bigger overarching symmetry, to create a so-called grand unified theory. And the hope would be that when you join these different symmetries together, the joining process places new constraints upon the individual particles created by the symmetrical constraints, and you have new ways to test what's going on. So in the case of the weak and the electromagnetic interaction, joining those symmetries together predicted that new particles had to exist, the W and the Z bosons, that were found at CERN long ago now. So this overall perspective on nature is the reason why the first person we stopped and asked at the beginning of the talk about the universe, was it simple, was it complex, thought that the world was simple. So the particle physicist looks at the world at the level of the laws of nature, or the symmetries which create those laws. And here's a rather brief picture of the history of physics, a sort of picture that's created by physicists rather than historians. So everything is a success, okay, there are no sidetracks, no failures, and it goes from about 300 years ago to the present. And what you see in this picture is the way in which things which were thought to be different are gradually shown to be really closely linked or the same. So once upon a time, people thought that static electricity was a different phenomenon to dynamic electricity that makes currents flow. But then it was shown that these are just different aspects of the same physical interaction. Similarly, Newton is demonstrating to us that the force that makes the heavens move around, that gives us Kepler's laws, is the same as the force that makes apples fall from the tree and keeps our feet firmly on the ground. So celestial and terrestrial gravitation, different aspects of the same force. In the 20th century, radioactivity and strong nuclear forces are found. The 19th century, Maxwell shows you how electricity and magnetism are really one and the same phenomena. So this unification of things that you think are different into single symmetries is the picture of progress in physics. And the electromagnetic and weak interaction unification of Glashow, Weinberg, Salam from the late 1960s is occurring here. These lines which are solid are parts of this unification picture which are completed in some sense, which are tested and well accepted as being part of the correct story. The dotted lines show you steps which are speculative in the sense that there are many ways in which you could take that step, and there is no decisive experimental confirmation that the right step has been taken. So we look still to find how to produce a quantum version of gravitation, how to link the electroweak and strong forces into one symmetry, and then ultimately how to join gravity with our grand unified theory into a so-called theory of everything. Superstring theory is the favorite candidate to do that, and we have a theory, as it were, to investigate, but as is so often the case, using symmetry principles to find the theory is a good deal easier than actually being able to solve the theory. So this is the perspective on the world that leads you to think that it's simple, that at the level of the laws of nature, the universe is very simple. There may just be a single final symmetry from which all these other bylaws, all these other symmetries derive. Well, so this is the basis for this single, rather Platonic view of the universe. And it's remarkable that if you talk to fundamental physicists about the structure of the universe or what they think is remarkable about it, what they think is remarkable is not something that any ordinary outside person sees at all. They're all impressed by the fact that there are beautiful stars and galaxies and so forth. But fundamental physicists are more impressed by the laws that lie behind the structures that you see. And we'll see a little bit more about that in a moment. Well, physicists don't have any unique perspective on symmetry or the liking for it. We have a natural human bias to like symmetry, and we look for it, we build it into physical theories. We presume that the universe somehow evolves or chooses it in particular situations. Well, the biologists and evolutionary psychologists have tried to persuade us that there are good reasons why we like symmetry, and we might even be a little nervous that we like it too much. So we see here in this beautiful example of the Taj Mahal how we build symmetry into architecture, and if we look in the living world, we see that lateral symmetry, left-right symmetry, is something that is characteristic of living things, and is a way of distinguishing them from inanimate objects, like a random rock or just a mixture of rubbish in your backyard. Well, people have argued that there's very good reason for that sort of thing. We like left-right symmetry because a sensitivity to left-right symmetry has an interesting evolutionary advantage long ago. So if you look into a crowded scene, you look into the forest, and you see something with extreme left-right symmetry, then more likely than not it's something with whom you might mate, or something you might eat for lunch, or worse still, something that might eat you for lunch. So if you don't have a sensitivity to that sort of symmetry, you are less likely to survive and pass it on than someone who does have that sensitivity. So I'd say you tend to live long and prosper if you notice symmetry. One other thing to say about laws of nature that one never sees said, which I think is rather fundamental, and that is everyone knows that Copernicus taught us that we shouldn't expect our position in the universe to be special in every respect. We have to be special in some respects. We can't occupy a typical position in the universe if a typical position in the universe has a temperature of 3,000 degrees. Okay, but we can't expect to be in a position that's special in every respect. But there was another revolution that was brought about by Einstein, which was not applied to positions in the universe having special status, but the laws. So Newton's laws of motion are un-Copernican, okay, and they're un-Copernican in a way that Newton certainly appreciated, that they only hold for special observers. So the only people that observe, say, that force is equal to mass times acceleration are observers who move in a non-accelerated way relative to the distant stars. So if you rotate, this picture I've drawn here, if you're in a spinning rocket and you look out of the window, you see particles and objects acted upon by no forces which accelerate, because you're seeing them counter-rotating about you. So you do not observe Newton's second law to hold in its simple form of F equals ma. So for Newton, there are special classes of observers for whom the laws of nature look simpler than they do for others. This is very unsatisfactory. Well, Einstein was deeply troubled by this, and he resolved this problem in the general theory of relativity. And again, there is a particular variety of mathematics that's perfectly suited to resolving this problem. So Einstein resolves Newton's problem by expressing the laws of nature using the language of tensors, so that if you have a law of nature that has the form t equals s, say, in one coordinate system, then if you make an arbitrary transformation of coordinates, the form of the law in the new coordinate system will be the same. So t primed is s prime. That is not the case for Newton's laws. So t prime will be s prime plus something else. So in the general theory of relativity, the forms of the laws of nature look the same to all observers, no matter what their state of motion. So this is an extension of Copernicus's principle to the laws of nature from simply the outcomes of the laws. Well, we've talked a lot about laws and the basis for a view of the world that's simple. But unfortunately, we don't observe laws of nature. No one has ever seen a law of nature any more than that they have seen the offside rule in football. You don't see laws and you don't see rules. You see the outcomes of laws or the consequences of rules. And unfortunately, the outcomes of the laws of nature are much more complicated and much more difficult to understand than the laws themselves. So you can see this rather easily. Suppose that we just balance this ball on the point of this pyramid here. Then in this position it's perfectly symmetrical. And the law of gravity that dictates how it will move, whether it will fall this way or this way, is perfectly symmetrical with respect to direction. It doesn't prefer balls to fall in that direction towards Rome or in that direction towards Albania. So it's entirely democratic. But nonetheless, if you create a quantum fluctuation that's intrinsically random, the ball will fall in one direction or another, and the symmetry of the law will be broken in the outcome. So we all occupy particular positions in the universe at the moment, but the laws of gravity and electricity and magnetism that govern our structure do not have any special preference for particular positions in the universe. But those symmetries are broken in the realization of the law that is you or is me. So this breaking of the symmetry means that the outcomes of the laws of nature do not possess the same symmetries as the laws themselves. That's very fortunate, because if the outcomes had to have the same symmetries as the laws, nothing would happen in the universe. There wouldn't be any structures, and we couldn't exist. So this simple observation, I think, is what I might dramatically call the secret of the universe. Okay? So it's how it's possible to have a universe that has unlimited complexity and asymmetry and symmetry in the outcomes of the laws of nature, and yet is governed by a very small number of simple symmetrical laws. Maybe just one, ultimately. So it's the fact that the outcomes of the laws do not possess the same symmetries as the laws themselves. So you begin to see now how it was possible for some of those people that we interviewed at the beginning to think that the world was complicated, and for others to think that the world was simple. It's a question of perspective. If you're a fundamental physicist, you have a rather Platonic perspective on the world. What interests you most are the laws of nature and the symmetries behind them. And so you tend to think that the world is simple because you focus on the laws of nature. But if you're a solid-state physicist, a chemist, a biologist, an economist, then you don't tend to talk about laws of nature at all. What biologist ever talks about laws of nature? They don't. All they're interested in is what things are stable in the long run. So which solutions of complex situations are the long-term stable outcomes? That is, they develop, say, by natural selection. So if you work in that messy world of competing complexity, you tend to think that that world of outcomes is complex, and you have a very Aristotelian approach to the world. So this is why these two views coexist. They're based upon different perspectives on the world. One on the laws and the other on the outcomes of the laws. Now, until relatively recently, probably 25 years ago or so, the educational process as well as research was very much dominated by this thread, and had been for thousands of years. Because this is the view of the world which creates examination questions that last for 30 minutes. It's exactly soluble problems that use special conditions, perfect symmetry, frictionless surfaces, all the idealizations which we're familiar with from teaching physics and mathematical physics to students or in high school. But a revolution occurred at the end of the 1970s that changed that. And that revolution was technological. It was the personal computer revolution. So before 1978, there were computers. They were very big and they were very expensive. And they were looked after by ferocious research groups with millions of dollars or pounds of funding. And they were dedicated to blockbusting projects like exploding stars or bombs or predicting the weather or the economy. And they involved huge teams of people. And they were cumbersome and complicated to use or to change or to program. But the personal computer revolution suddenly, for a relatively small amount of money, gave anybody the possibility of doing experimental mathematics, of looking at a complex system experimentally and just seeing what happened. So you no longer were constrained just to look at exactly soluble problems or easily approximatable problems. You could study problems with considerable complexity and interactivity just by looking at what happened. And so it was no coincidence that around that time there began to grow up in the world of mathematics in particular of chaos and complexity, aided by an ability to do experimental mathematics easily, inexpensively, individually, with good interactivity and very good computer graphics. So this study of complexity then has gone on and blossomed ever since. Complexity, I think you can divide into two categories. It's a bit like crime. It comes in the organized variety and the disorganized variety. Well, at first, disorganized complexity was the easiest to study, and this was given the name of chaos very early in the game. Chaos is simply the dramatic sensitivity to ignorance. So if you have a little bit of ignorance of the position or the behavior of a system, then very quickly that ignorance will grow exponentially quickly. We're familiar with this with weather systems and so forth. It's not generally appreciated that the first person who really put their finger on this phenomena and understood it very clearly was James Clerk Maxwell. And in 1873 in Cambridge he was asked to give a little talk on determinism to a group which was subsequently written up and published, and people were hoping that he was going to talk about Darwinian evolution and the extent to which you could predict the course of human evolution. But he talked about something rather different and much more interesting, and it was the extent to which the predictability of Newton's laws, which people regarded with almost religious reverence, was an illusion, and that in the future we ought to study what he called the singularities and the unpredictabilities of nature, and these would be much more interesting and important than the regularities. And he gives a very simple, nice Victorian illustration of a railway point where if you make a very small change with the switch of the point lever here, it will produce a completely different course for the train in the future. And he says here the existence of unstable conditions renders impossible the prediction of future events if our knowledge of the present state is only approximate and not accurate. Here's what he was talking about. Imagine we have a universe that's governed by one law, and that law just moves this point around this circle like a clock face, and the law just doubles this angle at each step. So this universe is completely deterministic in principle. If you know the initial position of this point, then after any number of applications of this law, you will also know exactly the position of the point. But in practice, it is not deterministic, because any initial uncertainty in the position of the point also doubles with each application of the law, and after about 15 applications of this law to this circle up here on the screen, an uncertainty equal to the radius of a single atom would be bigger than the circumference of the whole circle. And knowing the law doesn't help you at all to make future predictions about the position of the point. All you can say is that in the long run, there is an equal chance of being at any point on the circle. So what you learn from this situation is that there is this chaotic sensitivity to ignorance. Well, this type of disorganized complexity and chaos is pretty well understood. It's fairly ubiquitous in all sorts of different areas of science. But what is not so well understood are some other aspects of this story. At first, this type of unpredictability might seem very mysterious, and in many popular sort of journalistic treatments of science, you then saw people saying, this is the end of all science, because how can we predict anything? Well, the reason that we can predict things is because we can deal with averages. So if, like Maxwell, we were interested in the molecular motions of nitrogen and oxygen molecules in this room, then their collisions with other molecules and with the ceiling and the walls are chaotic in Maxwell's sense. And so we can't know anything about their trajectories with any certainty. And yet, when we're at school, we learn things like Boyle's law, that the pressure times the volume divided by the temperature is a constant. So how is this possible? Well, these quantities in Boyle's law are averaged quantities. So the temperature is a measure of the average speed of the molecules. The pressure is the average force per unit area on the walls of the room. And the volume is a fixed, large-scale, extensive property. So in many chaotic systems, the statistical distribution of the motion settles down to an equilibrium distribution. And there is what mathematicians would call an invariant measure for the process. So just because a process is chaotic and unpredictable in the small doesn't mean that it's chaotic and unpredictable on average in the large. The first person who appreciated this, incidentally, was Florence Nightingale, who is rather well known as a pioneer of certain nursing practices in the Crimean War, great British figure of the Victorian age. But it's not widely appreciated why she was able to make those innovations and developments in nursing practice and medical hygiene, and it was because she was a mathematician. She was one of the founding fellows of the Royal Statistical Society, and it was statistics that she used in a serious way to try and develop an understanding of what measures were effective and what were not. And it was Florence Nightingale who first commented on the design arguments that were popular in natural theology of the day, that the world was so wonderfully harmonious, so beautifully constructed to allow life to exist and persist into the future. And she pointed out that a key part of that mystery was the fact that the fine balance of conditions once set up maintained itself on average in the long run. And why was that? So why were there roughly equal numbers of males and females being born? Why was the stability of the Earth's structure stable over long periods of time? Well, so much for disorganized complexity. What about organized complexity? This is a much more challenging problem, and you can see why if you look at this picture here. This little graph of lots of things that we see around us in the world, and it's plotted in a type of computer speak. So instead of size along the bottom, we've got memory capacity, so how many bits of information can you store, and up here is computational power. that's nothing more than the ability to change one list of numbers into another list. So how quickly can you do that? And there are some objects which don't store very much information, but can transform it into other forms very quickly, like radio and TV channels. So they receive some digital signal and they change it into pictures very quickly. But they're not storing huge amounts of information like the Oxford English Dictionary or human DNA or the British Library. So these are structures which don't do a lot of fast transforming of information, but they store lots of it. But if you walk up the diagonal here, you find the things that are most complex in our experience, and complex in the most interesting way, because they combine the ability to store lots of information with an ability to transform it rather quickly into other forms. Everything on this picture is far from equilibrium, and so knowing why these structures exist is something of a mystery. You can't use ordinary close to equilibrium statistics to say what's the probability that life exists, or that a computer would spontaneously come into being, or that a flame exists. Flame is a nice example of a structure which is highly ordered, and yet it is very far from thermal equilibrium. So if we knew our great theory of everything that the particle physicists promise us, suppose we knew that string theory in great detail and we knew how to solve it, then it wouldn't help us understand any of the structures on this picture. Because what matters about these structures is not what they're made out of. They're all made of atoms and the same elementary particles that string theory would tell us had to exist. But what makes these structures interesting and different from each other is the way that those particles and atoms are organized. And it's the wiring diagram, if you like, the network structure, which makes these objects more than the sum of their constituents. So that's a defining feature of these objects, that they are more just than the sum of the atoms which make them up. It's the way in which the atoms are organized that makes them what they are. Well, if we pass on quickly, we might just finish by focusing on one area that was of great interest some while ago and has evolved off in different directions, where people tried to understand if there might be just a single generic type of complexity which could capture everything on here and other things as well, and in particular how that complexity could develop. Well, I think that quest was overambitious. There isn't just one type of complexity and there isn't just one way in which complexity can develop. But one way that was explored is rather interesting, brings together the features of the chaotic unpredictability with this type of organized, stable, complex structure. And there are three very different phenomena, sand piles, rivers, and lastly, a picture, dogs going for a walk, that show you why you expect to find links between things that superficially are very, very different. And the nice example that Purbach introduced a long time ago was that of a sand pile. Better to use a pile of rice in practice, but don't use a powder, behaves very differently. And Bach's intuition from observing these structures was that if you allow a stream of sand grains to fall onto the ground, then each individual grain is following a trajectory which is chaotically unpredictable. So a little change in the trajectory here will decide whether it goes down this side or down that side. So each individual trajectory is chaotically unpredictable. But if you keep dropping the sand grains, first you have a small pile and gradually the pile will steepen, but eventually it will get no steeper. So there is a final maximum steepness, and after that, if you add more sand, you'll simply produce more and more avalanches of sand of different sizes, and it's those avalanches, those instabilities, that maintain the overall organized, stable structure of the sand pile. If you do this on a table with a boundary, then sand will eventually start falling off the edge of the table at the same rate that it is falling down onto the top of the pile. So this is a sort of transient, stationary rather than static state. And as time goes on, different sand grains will be making up the constitution of the pile, even though the same overall structure holds. So this is like looking at a traffic jam because there's a blockage on the freeway from the air. You always see the same density wave of cars enhancing as it reaches the obstruction and then moving away, but there are different cars in the traffic jam at any given time. So there is a density wave of cars that's a stationary state. Well, Bach taught us that we should think of this situation as being a critical state, a self-organizing critical state. It's always on the verge of instability, so there's a little build-up of sand, then there's an avalanche, another build-up, an avalanche, and the key feature is that it's self-similar, that is, there can be avalanches of all sizes. In practice, the small avalanches will be more frequent than the large ones, but the fact that the frequency is just proportional to a negative power of the size, is what makes it self-similar. So if you have a powder, or there were rather sticky lumps of material that tended always to produce avalanches of one particular size, you wouldn't get this type of behavior. So this was Bach's original hope, that this might be the way all types of complexity develop. It's too ambitious. That really wasn't the case, but we'll see in a moment there are one or two other situations where it does seem to apply. Well, complexity is something that doesn't only have a place in science. Perhaps it also has a place in art. And this type of critical behavior that we see here, where the situation is on the verge of instability all the time, and the instability maintains the overall structure, is something that always really reminds me of what is interesting and appealing about some great aspects of art or music. If you have complexity and you apply reductionism, then you have what we call science. But I think if you just have complexity but no reductionism, you don't want to try and explain it in some way as being due to something else, then you have what we tend to call art. So what's the link with criticality? This sensitivity to small changes is something that's very important in some type of artistic experience. If you want a simple way to say whether a play or a book or a piece of music is good or bad, rather subtle question, my answer would be, it's good if you want to read it or listen to it or see it again. If you don't, it's not. So John Cage's 4 minutes 33 seconds of silence, which I was involved in the Italian premiere of at Parco Musica in Rome with Federico Einaudi last spring, rather amusing occasions, part of something else, is an interesting experience, but you wouldn't want to experience it again once you've had the idea. It's 4 minutes 33 seconds of silence, by the way. That's 273 seconds. And I think his idea was this was like minus 273 degrees centigrade, absolute zero of sound. But if you take a Shakespearean play, a great Beethoven symphony, a novel by a great writer, we say they're great and they're good because if you change the performance of that play very slightly, so you have different actors, different direction, different costumes, different audience even, then you get a completely different experience. So a great musical work with different performers, small change produces a different experience. adaptation of a novel for television or for theatre, again, small changes can produce a different experience. So there's a way, I think, of thinking about artistic experience as being ideally critical in this sense, where small changes give you another worthwhile experience. Well, someone gave me this picture some years ago in Mexico. There seems to be a rather famous artist there, Gabriel Orozco, who has even picked on the sand piles as his primary representation of art. Well, what about the rivers and the dogs? Well, just to show you that the sand pile is not just about sand piles, there are other types of self-organization in nature, which we see here. If you went to school when I did in England long ago and you did geography, there's only one thing you remember about geography from being at school in the 1960s, and that's Oxbow Lakes. Everybody knows about Oxbow Lakes. And I always tease my geographer friends at Cambridge, who are now very high-powered. You know, they're modelling climate, they're doing mathematics, whereas when I was at school, geography was about Oxbow Lakes and name 3 rivers in Africa. So they were the examination questions. So that's where the subject went wrong. So you see here a meandering lake on a relatively flat plain gradually produces these highly curved shapes, and eventually, as you remember from your school days, these will cut off. So the curvature will become so great that the flow rate falls, and so here is a part of the meandering river that's been cut off. So it's now a so-called Oxbow Lake. So this process is a way in which the river organizes itself and becomes straighter again. So the river once went sort of round here and round here, but now it's become straighter because it's cut off the Oxbow Lakes. So it's like the sand pile. You get steeper and steeper, little avalanche. Steeper and steeper, avalanche. So here the force acting is centrifugal, and the river gets more and more curved, more and more curved. Oxbow Lake forms, the river is straighter. Then starts to get curved and curved and curved. Oxbow Lake forms, becomes straighter. So this is a self-organizing process. It's just like the sand pile. So why are there such analogies? I think, see here on this cartoon, here's the original river. Pieces of high curvature get separated off, leaving the straighter trajectory. Well, why do you have that type of commonality? It's a nice cartoon that illustrates why it is. So we have a situation with the sand pile and the river where there is a force acting. In case it's gravity, other centrifugal. And there are a number of different equilibrium states into which the system can sit. But the force makes it move from one equilibrium state to another, and to do so in a particular way. So here is an analogous problem. There is a force acting, elastic, and there are a number of different equilibrium states here. And the dog is being pulled, and at first it goes uphill rather slowly. So it's pulled rather slowly. It's like the build-up of the sand, and then when it reaches the top, it jumps across. Avalanche. So growing curvature in the river, growing curvature, Oxbow Lake forms. Gradual build-up of sand, avalanche. So this type of structure of many equilibrium states with a force applied to it, you can see is a recipe for the development of a certain type of complex evolution. So finally, last picture. Our first question was the world simple or was it complicated? Here's a little picture which divides what we see in the world and what we do in science in a straightforward way. So here is a measure of the complexity of the things that we see and that we have to deal with. And here is a measure of the uncertainty or ignorance that we have about the mathematical equations or the laws which govern the phenomena. So in some situations, doing simple engineering and chemistry down here, where complexity is simple, is low, and the laws we believe are known, we have most of our very effective prediction, engineering structures, and so on. But if we go along here, we look at the dynamics of the solar system, turbulence in your bathtub, predicting the weather, we know what the laws are. There is no mysterious force acting in the weather system that's unknown. But the complexity of the phenomena, the sensitivity to ignorance is so great that we're rather poor at predicting the long-range future. If we go up here and we look at the Large Hadron Collider, then the basic phenomena are rather simple. Interactions between two particles producing another two particles. There's a huge number of them, but we have ignorance regarding the fundamental laws of high-energy physics and quantum gravity that are behind those relatively simple phenomena in cosmology and particle physics. If we move up here, above this dotted line, we're in very difficult situations of high complexity, predicting the future of climate, for example. And if we move up here, we have situations which are unpredictable in principle. So you can't predict the future of the economy or the future of your individual behavior if I make that prediction known to you. I can predict your future behavior faultlessly, in principle, as long as I don't tell you what the prediction is. But once I tell you the prediction, you can choose to falsify it. So, for example, if one of your politicians were to stand up on the television, I'm sure they never do anything like that. As an aside, the other day I was talking to Robin Wilson, who's a friend of mine. He's the mathematician, but he's the son of Harold Wilson, who was the former Prime Minister. And all the other members of the family were teachers of mathematics and other things. And Robin said his father, Harold, said he didn't go into teaching because there was too much backstabbing, so he decided to go into politics instead. So if one of your politicians were to stand up and make a prediction about the future of the economy, that will change the future of the economy in a way that the prediction cannot logically completely include. And similarly, if you make a prediction about the course of the election, you carry out an opinion poll, and you publish the result of the poll, it alters the course of the election in a way that cannot be completely included in the poll. So these problems up here are of a different sort. They are intrinsically unpredictable in detail. You might still, on the other hand, find out that you're quite good at predicting the outcome of an election. And sometimes we are, and sometimes we aren't. You'll have much experience of this, I think, in coming months and years. Well, this brings me to the end. I hope I've given you some tour of simplicity and complexity, and at least enabled you to deal with questioners on the street outside. If someone asks you, is the world really simple or complicated? You'll be able to explain to them that it depends whether you're looking at the world at the level of laws or at the level of the outcomes of the laws, and what those different perspectives tell you about the world, and how mathematics is an integral part of understanding both those routes. Thank you.